Hello everybody, welcome to another lecture. Our topic for today is linear approximation. I have a formula down here that's going to be our main formula today. So what is this about? I'm actually just going to give this as a formula right now. We're going to do a few quick examples so we understand what the goal is, what the kinds of typical problems are today, and then we'll try to discuss why this is a formula that makes sense. So suppose that you have a function f that is differentiable at a, meaning f prime of a exists. The derivative exists at this point. Then the linear approximation around a, we define that to be this function L of x, where x appears right here. It's just multiplied by f prime of a. Everything else in this formula is just numbers. F of a itself, and f prime of a. If you have a specific function f and a specific number a, those are going to be just parameters, just numbers. So this function is a linear function. The dependency on x is very simple. That's what I mean. And the significance of this function is that is right here. F of x is approximately equal to L of x. That is, L of x approximates f, at least when x is close enough to a. So you always need this a, which you can think of as a base point for your approximation. And then when x is close to it, the function L defined up here is a good approximation to f. That's the idea. So here is a typical problem where we're going to apply that formula. Imagine the function is x cubed. Item A is saying find the linear approximation L around a equals 2. And then use that to find the approximate value of 2.01 cubed. Then they're also saying calculate the actual value to see that this is going to be a good approximation. So let's try this. So the function was given as x cubed, and the point A in item A is here a equals 2. In order to find the linear approximation, we need the value of the function on the point A. So f of 2 in this case, that's 8. And we're also going to need the derivative at that point, f prime. So find f prime of x first, a formula for the derivative. At any x, in this case, x cubed becomes 3x squared by the power rule. So that then you can find f prime of the number a, which is 2 in this problem. You basically plug in 2 into the formula, 3x squared. And that's a 12. So what does that tell you about the L of x function? Remember the formula, it's a similar formula to the tangent line. It's basically the same. I mean, this is actually where the motivation for this concept really comes from, as we will see soon. This is the formula. So L of x is f of a is 8, f prime of a is 12, x minus 2. This is the linear approximation function. Now, if you want to find an approximation for any point close enough to the number 2, like 2.01 that was given in the problem, it's very simple. You're going to approximate that by L of 2.01, which you just compute from here. 8 plus 12, 2.01 minus 2, the formula that we just found for L. So you see that this is 8 plus 12 times 0.01. That's 0.12. You're basically dividing by 100 when you multiply by 0.01. So you find the value 8.12. This is the approximate value. And by the way, the actual value that the problem was also asking, just for comparison purposes, if you use a calculator, the actual value is 8.120601. So it's close, but it's not exact, of course. Okay, now item B, I'm going to scroll back up so we can see that again. It's a similar one. Same function. We're not using a different point, a equals minus 1. Then we want to use that to approximate the value of minus 2 cubed. And then also calculate the actual value to see that this approximation is not going to be so good. We do not expect this to be a good approximation for -2 cubed because, well, essentially the point where we are basing the calculation, the a value is kind of far from -2. It's -1. But anyway, of course, we don't need any approximating schemes to find the value of this number, -2 cubed. We know what that is. But we're just trying to use the L of x function. That's the point of this problem. So a is going to be -1 now. So once again, we need to find all the parameters here. F of a. F was the cube function, so that's also -1. And f prime of a, that was the 3 times x squared function. So that's 3 in this case. The linear approximation function is then f of a plus f prime of a times x minus a. A is -1 now. So I'm just going to replace this -1 with +1. That's L of x. Then if you want to use L, this L function based at the number -1 in order to compute -2 cubed, which is f of -2, then according to this formula, you would get this number. I'm plugging in -2 into the formula for L of x up here. So what do we get? -2 plus 1 is -1. So -3 with another -1 outside. That is giving us a -4. This is the approximation that we get, whereas the actual value of f of -2, which means -2 cubed, is actually -8. So as you can see, the values are not close this time because the a point was close from the x point. All right, so the typical problem of using a linear approximation will ask for something like this, where it's a thing that you cannot really do on your head. In your head, you have to use a calculator. Look at this problem. Use linear approximation to find an estimate for the cube root of 7.96. When you see this, you need to identify a function that you're trying to compute. And you also need to identify a closed value that you know how to compute. In this case, solution. If you think about f of x as the cube root function, then you're trying to find cube root of a specific number, 7.96. But you know it for a very close number to it, the number 8. Cube root of 8 is 2. So this 8 should be your a. It should be the number where the linear approximation is based. Let's try to find this linear approximation function now. Well, we know that we're going to need f prime, so we can go ahead and find that first. To find the derivative of the cube root, just remember that's the same thing as x to the 1/3. So you need to apply a power rule. It becomes 1/3 times x to the -2/3, which is 1/3 minus 1. Okay, so f of a is the cube root of 8. That's 2, as I said. F prime of a, well, you plug in 2, which is, sorry, 8, which is a, into the formula for f prime. So this is a number that we know how to compute as well, because that's the same thing as just rewriting this 1 over because of the minus sign in the exponent, cube root of 8 squared. Well, 8 squared is 64, and the cube root of 64 is 4. 4 cubed gives you 64. So in other words, this is 1 over 12. An easy number to find. With those parameters, you have a formula for the linear approximation. Always like this, f of a plus f prime of a times x minus 8. So we can find now f of a, I mean not find, but replace, we already know these values. F of a is 2 right here. f prime of a is 1 over 12. And x minus a is 8. So continuing now, I mean, we can leave the formula like this. This is the linear approximation around the number 8. This is a good approximation for any number close enough to 8, like the one given in the problem, 7.96. I think it was 96, yes. What is the value of that? Approximately L of that, which is 2 plus 1/2 times 7.96 minus 8. Sorry, it was not 1/2, it was 1 over 12. Yeah, I need to fix this. That's better now. The value of f prime of a is 1 over 12. So, okay, 2 plus, well, 7.96 minus 8 is a negative number, so I'm going to write minus here. It is 0.04 over 12. This is not really going to be a decimal that we know that we can find easily, but I mean it's not a finite decimal. That's what I mean. It's going to be something divided by 3, but we know what that is. 0.03333. That gives you this decimal 0.01 divided by 3. So you find 2 minus that 1.997. That should be right. But when we finished up here, this would already have been a good answer. I'm trying to compute these decimals in my head down here. I may have an arithmetic mistake or not. You should check. But the point is that this is going to be a pretty good approximation to this cube root of 7.96. You should try to find it with a calculator now to compare the results. But anyway, let's move on to another problem. This is very similar. Use linear approximation to find an estimate for this number. 0.13 to the minus 1. So what we have to consider here is that we need to know a number close enough to here where we know how to compute the function. So first of all, what is the function? Well, the operation that you're trying to apply to a specific number in order to approximate it is the raising to minus 1, which is 1 over the number. That is the function here, 1 over x. So because that's the same thing as x to the minus 1. We are trying to apply that to the number 0.13. We need to find an a that's close to that where we know how to find this number. You're not going to use, for example, a equals 0 because then f of 0 does not even exist. All right, the function f has to be defined there. So even though 0 is close to 0.13, we don't use that. A better choice here, there isn't just only one, but usually there will be one very obvious, and it's this one, 0.1. Because f of a is the inverse of that. This number right here is the same thing as 1 over 10, right? It's 1/10. So the inverse is 10. So let's use this as our a. Well, f prime, we know that we're going to need that. That's minus 1 over x squared, again by the power rule. So that when you find f prime of a, that's going to be minus 1 over 0.1 squared, which means minus 1 over 0.01. Well, that's the number 1 over 100. The inverse of that will give you 100. And there's a minus sign from the derivative formula. So, okay, with these parameters, we have a pretty good approximation for right here. For f of x around any number close to a. F of a is 10. F prime of a I just found as 100. And then x minus a is x minus 0.1 or 1/10. So yeah, be careful that, for example, when you evaluate the function and the derivative, notice that we evaluate those at the number a, not at the number that would be 0.13 in this problem. That is the number that we're going to plug in for x now, not a. So 0.13 inverse the thing that we want to find, which is f of that. F is approximately L, and L is equal to this particular expression, 0.13 minus 0.1. How much does that give you? Just 0.03. We're going to multiply that by 100. So 3, and that's a 7. Well, the inverse of 7 is actually more like 0.142 or something like that. It's a close number to this, so we know that the answer makes sense. The inverse of this number should be very close to 7. This is linear approximation. So why does this work? Let's talk a little about that. If you haven't realized yet, the connection is with the tangent line. Why does this work? Well, the tangent line to the graph at the specific point with x coordinate equals a, we already discussed this topic, right? The equation of the tangent line is this one. Y equals this particular expression for x. That is the same thing that we just defined as L of x. So the idea is that if you think of this as a function, instead of y, you write L of x, then this function is gonna, the graph of that is gonna be a line, the tangent line, and the tangent line stays close to the original function when x is close to a. That's the whole idea. So imagine you have a function that's the blue line here, and you're talking about a number a, and also about a number x very close to a. Okay, I should probably erase this x. It looks like an exponent here, a to the x. That's not what I mean. You have two numbers, a and x. Well, if you zoom in into this picture right here, so I'm looking at the zoomed in version, you see that the graph in blue and the tangent line in red, they meet at the point where the tangent line is based. That's the point A. But if you're close enough to there, then the value of the blue line and the red line, they're really close. So the tangent line L of x and the actual function f of x, they're also going to be very close. This is why linear approximation works. And we can, in fact, we can say a little bit more. If we talk about this notion of concavity, then we can say that L is going to be either above or below the graph. So let's briefly discuss this. Concavity, suppose you have a differentiable function at a point A again. We're going to say that f is called concave up if the graph has a U shape around this point A. And then concave down if it has an upside down U shape around A. Usually you want to think of them as smile and frown. So let me show you the picture before we discuss the connection to the second derivative. Like this. You see that this is just one function and two locations, two possible A locations. Around the first one right here, the graph is a frown. It's an upside down U. So the function is concave down at this point A. Whereas a point A right here on the right side of the graph, the function would be concave up there because the graph has a shape of a smile. And you see that, by the way, we're going to discuss this further in a future lecture, but there is a connection to the second derivative. When this, if the second derivative exists, so if the function is twice differentiable, when f double prime of A is positive, that means smile. This particular case here, so concave up. Whereas if the second derivative is negative, that means a frown or concave down. So just be aware of this connection. We're not really going to use this today, but you should know that this exists. This is a interpretation for the second derivative. But for us, what's going to be important is this fact that if the graph is a frown around A, concave down, then the tangent line around that number is always going to be above the graph, which means that the approximation L of x for an x close enough to A is going to be larger than the original function. As you can see from the picture, the red line is above the blue line. I wrote larger than or equal because technically, like, the function could be a line, so the tangent line is equal to the function. But yeah, usually you're going to see a strictly larger. Whereas now looking on the other half, if you have a concave up function around the point A, and you look at an x close to it, then the tangent line is going to be below the graph. So the linear approximation is below the graph. So basically, this is what I'm saying in this box down here, concavity analysis. Once again, suppose the function is differentiable at the point. If it is concave up, then the tangent line is going to lie below the graph, which means L of x is an underestimate, which means L of x is smaller than the actual value f of x. And similarly for the other case, if the function is concave down, the tangent line lies above the graph, so L is an overestimate. So why do we discuss this? Because now we have problems like this one where not only we want to find an approximation, but we also want to say if it's larger or smaller without using a calculator. So here is the problem. Let f of x equals ln x. I drew the graph down here, but this is a graph that we should always remember, the graph of ln. It's defined only for positive x's. And it looks like this. The overall shape of this graph is concave down. It's a frown, right? Because this is a curve that's going down. It doesn't have to, complete the motion, go fully down like this. In this case, the function just keeps growing forever, but with the shape of curving down. So let's look at item A. Use a linear approximation around the point A equals 1 to find an approximate value of ln of 1.1. So this is just like the previous problems from today. We can do that. The function is ln x. A is equal to 1. So f of A is ln of 1, which is 0. And well, what is f prime of a general point x? The derivative of ln is 1 over x, which means that we can find f prime of A as 1 over 1, which is 1. So with the parameters, we can produce L of x. L of x is f of A, which is 0, plus f prime of A, which is 1, times x minus A, which is 1 again. So this just becomes x minus 1. All right. So basically, imagine now the tangent line around here is the point 1, the place where ln is equal to 0. The tangent line and at that location is the line y equals x minus 1. It makes sense, right? This looks like what this line would be. Okay, so this is ln of x. F of the number that they asked about was 1.1 is approximately L of 1.1, which is 1.1 minus 1, 0.1. This is the approximate value for ln of 1.1. But finally, B is saying, do you think this is larger or smaller than the actual value? Answer without a calculator. Okay, basically looking at the graph, you don't even need to know where 1.1 is or whatever. You just have to understand, because the graph is curving down, the red line, which is the linear approximation, is above the blue line, which is the graph. So we would say that the linear approximation that we found is above the actual value of the function, because ln x is concave down. Technically, we just need to know that this happens around the number a equals 1, but in fact, it happens everywhere on the graph of the ln function. It's always concave down. So this is an acceptable answer already. The actual value is going to be smaller. So it's actually going to be more like 0.09 something. So let's do another one like this. Once again, 2 items. Answer without a calculator. Find the linear approximation to cosine x around the point a equals 0. And then estimate cosine of 1 degree. Is the actual value larger or smaller? Okay. F of x equals cosine. We know that we need f prime, which is minus sign. A was given as 0. F of a is then cosine of 0, which is 1. Think about your unit circle if you need. And f prime of a would be minus sine of 0, which is 0. No derivative there. Okay, so what is the linear approximation function based on these parameters? F of a plus f prime of a times x minus a. You see that this is just a 1. The linear approximation is a constant function. L of x equals 1 for all x's. Why is this happening? Well, we found a 0 derivative, all right? So there is no slope of the tangent line. It is a horizontal line, which means a constant function. So basically this right here is telling you that cosine of anything close to 0 is equal to 1. In particular, the cosine of 1 degree, that is approximately L of 1 degree, which is 1. L of anything is 1. That is your approximation. Not a very useful one. This approximation would give you 1 for any small angle. That is not very useful. But what is going to be useful is knowing at least, is that actually larger or smaller? Well, in order to understand that, draw the graph of cosine to really see what it's doing. This is once again a graph that we should remember. Cosine, we know it's the oscillating wave like this. It starts as 1 when x is 0. Then the first time when cosine becomes 0 is pi over 2. And then cosine of pi is minus 1. This is the graph of cosine. In this item, we're talking about a equals 0. So around that point, cosine is a frown. It's a function that's concave down. Now, if you think about the tangent line, which is horizontal in this case, the tangent line is above the graph because the graph is concave down. The linear approximation that we just found is the value on the tangent line. It's the red graph. That is larger than the actual value that we want, which is the blue graph. Here is 1 degree. So it's a little bit smaller actually. Cosine of 1 degree is a little bit smaller than 1, which is the linear approximation, because the function cosine is concave down around this number 0. Now for item B, it's going to be basically the same thing, but I realized something. I want to change the value on the problem. This 177, I don't want to do another problem where the tangent line is also horizontal. I want to do it with an actual tangent line. So I'm going to change this value to 147 degrees. Change that in your notes, please. Let's solve problem B now. B is asking cosine of 147 degrees. What is it approximately? And the actual value, would it be larger or smaller than this approximation? The point being that because this is degrees, but when you talk about derivatives and so on, the trig functions should always be in radians. The argument of the trig functions is always radians. We're going to need to convert this. All right, so first of all, before we even think about that, what is a close enough value to this angle where we know the value of cosine? 150 degrees, which is, well, 5 times 30 degrees, so 5 pi over 6 in radians. Let that be your A, because then A is equal, cosine of A is equal to, what is the cosine of 150 degrees? Think about your unit circle. It is a negative value, root 3 over 2. That's the same as cosine of 30, but negative. Okay, so we have cosine A. The derivative, that's f of A, right? Now f prime of A, we already know the derivative is minus sine. So minus sine of 5 pi over 6, or 150 degrees. Sine is positive 1/2, but with this extra minus in front, that becomes negative 1/2. That's, yes. All right, so we have the parameters here. The linear approximation function based on this point, where everything has to be in radians. Once again, if you have a problem involving derivatives and trig functions, everything should be thought about radians, in terms of radians. So even this x here. Now L of x has to be approximate. Well, L of x is actually equal to, that's the linear approximation, f of a minus root 3 over 2, f prime of a minus 1/2, x minus a is 5 pi over 6. Okay, now the x number that we have, 147 degrees, let's convert that to radians. To convert degrees to radians, what you have to do is multiply by pi and divide by 180. That's basically what this is. We can do one simplification here if you divide by 3. But that's not really needed. The final answer is going to have a pi in it, so it's not like we're going to convert to decimals or anything. This is the actual x where we want to find the linear approximation. F of x, cosine of 147 degrees, that's going to be approximately the linear approximation at this point, 49 pi over 60. So according to our formula for linear approximation, just leave it like this. Over 60 minus 5 pi over 60. We can at least find this subtraction of multiples of pi here. Let's see, 5 pi over 6 is the same thing as 50 pi over 60. So this will give you a minus pi over 60 with another minus in front will become a plus. And then 2 times 60 is 120. So there you have it. The approximate value for cosine of 147 degrees is this. And finally, the last question they asked, do you think this is larger or smaller than the actual value? You just need to try to understand if cosine is a frown or a smile around that point. So once again, here is the graph. 90 degrees or pi over 2 is this first place where cosine becomes 0. And then pi or 180 degrees is right here. The angles that we have are between these two. Like we have right here 5 pi over 6 or 150. If we want to think about degrees, that's the A. The X is a little bit smaller than that, 147. But whatever, at this location where A is, around here, the graph is a smile. It's concave up. So we can say the actual value of cosine, the blue graph, is larger than the approximation that we found. Because if the graph is a smile, the tangent line, the red line, is below it. So because cosine x is concave up around a equals 150 degrees. Okay, so this was the problem. We just had to be careful with this idea that the x and the a's needed to be calculated in radians in all the formulas, because that's when we're talking about derivatives, when we're talking about calculus, this is how we actually define the trig functions, always with respect to a pure number, a radian, and not a number with a unit, which is the case of degrees. The next idea that we can get from graphs, this idea right here, this is saying by looking at how strongly the graph of a function curves away from the tangent line, you can also get an idea of how good the approximation is. So once again, I have a quick graphical example where it's the same function, blue line, but I'm talking about two different points A. You see that around the first point, in both cases, actually, the graph is concave up. And in both cases, I'm taking an x that is about the same distance from the A. Look at this distance between x and A, about the same. However, if you look at the graph of f around this first A here, this mile is very wide. So you can say the graph is not really, does not have a high curvature. It takes longer time to get away from the tangent line. So look at the distance between f of x and L of x. That's a really small number right there. The approximation is good for this x because the graph is not curving too much, so it's not getting away from the red line by too much. Meanwhile, around this point A here, because the graph has a strong curvature, even though the x is just as close to A as before, look at the actual value of f of x versus L of x, much further apart. So this idea can show up in problems like this. I'm going to give you two numbers to be approximated. I'm going to ask if they're larger or smaller, but then finally, which one do you think gives a better approximation? This type of question we can answer also by looking at the graph of the function, by looking at how much it's curving around that point. But let's focus on A first. Both of the numbers that we want to approximate, they are inverse of something. So the function that we were talking about is 1 over x with a derivative of minus 1 over x squared. In this case, let's call them A and B, the two numbers around which we are finding an inverse. What do you think they should be? Well, a number close to this one where we know an inverse is just 1. And here it would be 20. So let's say A is 1 and B is 20. Let's find the linear approximations around these guys. Quickly here, f of A is 1, f prime of A is minus 1. So L, maybe I call that L1, or even better, LA, the linear approximation around this A number. That would be 1 minus x minus 1, which becomes, if you want to simplify this, 2 minus x. Yes, okay, now the second one, B is 20. F of B is minus 1 over, it is 1 over 20. Why did I say this is an easy number to compute? Well, this is, if you want to write in decimals, 1/2 of 1/10, so 0.05. That one we can do very quickly in our heads. F prime of B, now I'm going to use this formula for f prime, minus 1 over 400, which is basically the negative of the square of this number. So that would be 0.0025. Okay, and LB becomes f of B plus f prime of B times x minus b. The linear approximation around the number given above. Maybe let's not simplify this one. So, okay, scrolling it back up, the two numbers that we're trying to approximate, 0.9992, 20.0008. So f of 0.9992 is approximately given by LA of that number. This number is close to A, which is 1. So that is just 2 minus that number, which we can compute very easily. That's 1.0008. This is the approximate value of the inverse of 0.9992. And the other one, 20.0008, that's close to B, which was 20. So we use this other linear approximation for it. It's going to be approximately LB of that number, which is 0.05 minus 0.0025 times that number minus 20. That just gives the decimal part. So that's, I mean, a lot of zeros here. 0.00000, and then 8 times 25 is 200. So just a 2 there. So 0.040998, something like that, should be the inverse of that number given. Anyway, that's the answer to A. We can move on to B. Are they larger or smaller than the actual values? Okay, what is the function? Once again, the function is 1 over x for both cases. This function is a smile. It's concave up. We don't even need to draw the points, the tangent lines, whatever. We can just say the, like, let me write, for example, f, the actual value of the function will be always larger than whatever approximation you use. Right, the approximation is the tangent line. Let me actually draw them so we remember. And the f is the blue line, the graph. So in this case, the approximations are smaller, or maybe let's write it to preserve the same order that I just wrote. The actual values are larger than the approximations. And why is that? Because f is concave up. So you technically don't even need this drawing in your answer. The fact that f is concave up should be something that you know, but I recommend always drawing, so really there is no confusion. Really, you should know why you're saying what you're saying. But then the final question, C was asking, which approximation do you think is better? The one for the number 1 or the one for the number 20? The answer here now disconnects us to the previous slide where we said the shape of the graph determines if the approximation is good or not. Not only how close the number a, the number x and the number a are, but also the shape of the graph. In this particular case, the number 20 is way large. It's all the way down there on the x, the positive side of the x-axis, where the function is basically horizontal. The function is going to be very close to its tangent line. So the graph doesn't have much curvature there. On the other hand, here, that's a different story. This is a location where the graph is kind of passing from horizontal to vertical. There is a lot of curvature there. So this means the function deviates from the tangent line much faster around the number 1. So we would say that the approximation to the first number is worse than that to the second number. I'm gonna write parentheses here because the curvature of the graph of 1 over x is, you can say larger, you can say stronger around the number a than around the number b. This is how you justify your answer.